Our speaker today is Gregory Henselman-Petrusek, and he will talk today about secular persistence. Stage is yours.
Well, thanks very much, Teresa, and thanks to all the organizers for the invitation to be here. I'm very excited to talk about this work, and I'm very excited to talk about directions that we're thinking about going in the future. To set the stage for our conversation a bit, first I'll say thanks to our various sponsors. And I'll frame the conversation by saying that this is a talk about persistence modules, and today a persistence module will mean a functor from a totally ordered set into a category. For simplicity, we will focus on finite totally ordered sets, so they might as well be the integers from 1 to n with the usual order. But in general, most results can generalize to much more complicated, well, much larger index categories. And we're going to be talking about decomposing persistence modules into interval modules. And by that, I mean a module that is 0 for a while, becomes possibly non-zero, carries forward with a bunch of isomorphisms, and then becomes 0 again. So this definition makes sense in any category. It doesn't have to be a category of vector spaces, for example. And when I talk about coefficients, usually I'll mean this as a byword for the target category. So secular persistence is a formal framework that allows us to decompose a nonlinear persistence module, for example, a persistence module of abelian groups, into interval modules. It's computable via matrix factorization. It has a range of applications. One of the most important is getting generators for persistent homology and homotopy, which makes generalized barcodes for persistence modules with non-field coefficients, interpretable and localizable in terms of the generating data. It suggests new algorithms for computing generalized persistence. And it has a variety of theoretical implications for extension problems, counting theorems, etc., and homological algebra and other fields. It also has connections in category theory, quiver representations, and homotopy. And one of the key ingredients to making this framework run is the idea of exact non-additive categories, which we'll touch on briefly towards the end. So if there's one theme I think everyone might take away from this conversation, it's that this application area is really just the tip of the iceberg as far as applications of non-additive categories in our field. And we'll discuss a bit at the end, perhaps why machinery from this field gives us things that we didn't know about before, and some fruitful future directions for work in this area. Okay, so the program today, we'll start with a bit of background on persistence over the last 20 years. Then we'll talk about secular persistence in terms that are hopefully fairly familiar, or that will become familiar to many folks on this call. And then we'll give another definition that's perhaps a bit less familiar, but that's highly extensible. And this is an exciting way to look at things because it seamlessly connects the ideas that are sort of key to persistence with ideas from this much bigger field of exact categories and homological algebra. And then we'll talk a bit about applications. So that's the program. Let's get started. To further motivate this work, let me say a few words about nonlinear coefficients in data and where they show up. So why, for example, might one care about torsion in homology with integer coefficients if you work in applications? Here's one example. There's a result by Costa, Farber, and Horak, which essentially says that within certain parameter windows, the clique complex of an Erdős-Renyi random graph will have high levels of torsion. You don't need to know exactly what an Erdős-Renyi random graph is. Essentially, you take some vertices and you connect each vertex with each edge with probability P in an IID fashion. But here's how this plays out in practice in one context, and I hope everybody will get ready to raise their hands in response to a impromptu group survey. Take two matrices, one whose entries are IID, say the symmetric matrices, IID real entries, and generate another matrix by generating a random point cloud of 1,000 points in Rn. Choose your favorite n. From there, plug your distance or your dissimilarity matrix into your favorite pH solver to generate filtration of Viator Strips complexes. And guess what's going to have the longer runtime. So let me see a show of hands who thinks it's going to take longer to compute the persistent homology for the point cloud distance matrix. I think you can use your reaction buttons. Okay, so nobody's voting for the point cloud, or perhaps I just can't see. Oh, we see one. Great, great. Very good. Okay, a couple. Very good. Okay, how about everybody else? We'll just make sure that everybody's actually listening. Who thinks the IID entries?
I see it.
Wonderful. Great. Okay, well, here's what you find in practice. If you run the point cloud distance matrix, your calculation will end very quickly, easily less than 10 seconds if you're using a fast solver. If you try to do the matrix with IID entries and you work with Z2 coefficients, then your calculation will run for days. And if you're working over the fields, the rational fields, you're likely to encounter an overflow error. And why is this? The reason is that probabilistically, the matrix with IID entries is very likely to generate a space with a huge amount of torsion. And this torsion shows up in the persistence calculation in the form of much more complicated basis matrices and algebraic operations that you need to run. So these things show up sort of in matrices that are pretty important to both mathematic and scientific daily operations. So in particular, you'll run into matrices with IID entries if you're doing hypothesis testing, because they naturally show up as a null distribution. They show up in unstructured data, they show up in random matrices, and in many other contexts. So there's one place that torsion shows up, and it's pretty common. Other common examples are blue chip data sets. So for example, natural images, one of the classic data sets in TDA. Klein bottles a space with a bit of interesting integer homology. Similar with smectic liquid crystals and orthogonal projections, some of the most classic examples that we like to draw on when we talk to people about applications of topology in data. There are also natural examples in homotopy. So if you have a filtered path connected topological space, in addition to the persistence module of homology groups, you can get persistence modules of homotopy groups, and in particular, persistence modules of non-abelian groups. So here you can see two examples of a filtered topological space, X and Y. They have isomorphic pointwise homotopy, isomorphic pointwise homology, and persistent homology, but they have non-isomorphic persistent homotopy. And one way that you can show this is to compute the secular barcode for each of these filtered spaces, and you can identify the fact that the two barcodes are distinct. We'll run over that in a bit more detail later in the talk. So non-abelian coefficients or non-field coefficients show up in homotopy. So there's a natural question: how do you analyze these persistence modules? They show up. You can't get around them. They can make your life very hard if you want to run calculations last minute for some kind of presentation and you have random matrices to work with. So what do we do? Well, there's been progress in this domain as early as 2017, 2018. Amit Patel, who is on this call, introduced this notion of a generalized persistence diagram for a persistence module. And similar to the linear story, this is a machine that will take in a persistence module, say of abelian groups. It can work in any abelian category, and depending on what your needs are, you can even do something a bit more general than that. And you can turn it into a persistence diagram that somehow represents a breakdown of your module into pieces. And it resembles classical persistence diagrams in many ways, except now that the points are labeled by isomorphism classes of objects in your category. So for example, in this diagram, we have 2 points that are labeled by a copy of the cyclic group of order 2. There are a few gaps that are still getting filled out in this theory. So the original formulation doesn't handle non-abelian groups. And if you're working with vector spaces of infinite dimension, which have recently become interesting in the context of certain geometric calculations and some really nice work on Morse theory in the singular setting, infinite dimensional vector spaces come up naturally, and you might want to ask, how can you work with them in a persistent context? And finally, the biggest point that we will try to fill in from the existing theory today is that the notion of the generalized persistence diagram does translate an interval module into a persistence diagram, but it doesn't give you a corresponding decomposition of the associated persistence module, which means it doesn't allow you to take a bar or a point in the persistence diagram and map it back to a cycle or a generator in data, which is important in certain scientific applications when you want to go to a scientist and say, we calculated these invariants, we found this interesting bar, and this is what it means. Typically, they want to say, okay, where does that show up in the spaces that I'm working with? And generators are sort of the key to do that, as well as the key to realizing a lot of connections with the wider range of tools that homological algebra has to offer and functoriality have to offer. So historically, these are some of the benefits that we saw from the first linear decomposition of persistence modules. There were benefits in terms of explainability in generators. Recently, there has been some nice work on relational knowledge, specifically analogous bars that were explored by Hiron, Yoon, Greist, and Giusti in a paper called Persistent Extension and Analogous Bars, although this is not at all the only work on understanding relationships between bars and a barcode. And historically, after the notion of the direct sum decomposition of the persistence module into interval modules really came into this field, we saw a lot of new algorithm development that allowed speedups and allowed ideas around things like duality that led to faster cohomology accelerations and other things. So there were a lot of advantages to getting this richer structure, both scientifically and computationally and mathematically, because once we saw these connections, we could make a lot more interesting statements about category theoretic structure, quiver representation, and then some interesting algebraic ideas that are now commonplace, like stability and duality and dimension reduction. Okay. So this all makes it attractive. We know that we have to encounter non-field coefficients in the real world. And there are a lot of reasons to want to understand those modules a bit better. So there's some background. Let me just quickly check how we're doing on time. Great. So now let's talk about definitions. What is secular persistence? Well, it's a way to decompose interval modules. So again, if you fell asleep earlier, that's great. You can wake up and no worse for the wear. Remember that a persistence module for us is going to mean a functor from the poset category of the first n integers, i.e. a finite totally ordered set, into some category E, and we'd like to decompose it. And as a warm-up, we'll start by decomposing an abelian group into simpler parts. And that's a task that we're a bit more familiar with in some contexts. When you talk about decomposing abelian groups, there are two sort of classic decomposition schemes. There's the Kroll-Schmidt scheme that decomposes a group as a direct sum of indecomposables. And there's the Jordan-Holder scheme, which is different in character. And instead of trying to get this direct sum, you get a nested sequence of subgroups. And then the components that you get out are the quotients of each subgroup by the subgroup that came before in the sequence. So people talk about composition series in connection with Jordan-Holder. And depending on which decomposition you use, you talk about the pieces that you break your object into in different terms. So for Kroll-Schmidt, we have summons, and for Jordan-Holder, we have so-called composition factors. And each decomposition scheme, as you would hope, has a sort of uniqueness result. So neither decomposition is exactly unique, but there are guarantees that the components you get out of each decomposition are unique up to maybe isomorphism and some sort of permutation. So these things pick up on different types of information, and each one gets something that the other one can't. Kroll-Schmidt is in some sense lossless because it preserves the isomorphism class of the object you want to work with. Jordan-Holder doesn't, in the sense that a group is not uniquely determined by its set of composition factors. So you lose some information when you pass to composition factors, but you can use them to break down things that you can't break down with Kroll-Schmidt. And so in that way, you can get a bit more fine-grained analysis. So that's going to be a mirror of the story today. And when you think about decomposing a persistence module with field coefficients, really what people think about is the Kroll-Schmidt decomposition. And what I'll tell you about today is a Jordan-Holder version. And like Jordan-Holder, you can use it to break down modules that you can't further break down with Kroll-Schmidt. And like Jordan-Holder, it is lossy in the sense that your secular factors aren't going to identify the underlying module up to isomorphism. You lose that data, but you get something a bit more fine-grained in compensation. So let's do a bit more warm-up. Suppose we want to decompose the abelian group Z20. Well, here's the Kroll-Schmidt decomposition. Break it down into Z5 plus Z4. And here's the Jordan-Holder. So remember, the way that Jordan-Holder works is you find a nested sequence of sub-objects. And if you like, you can draw them on a line. I like to do that. And the key thing about this decomposition is you need the quotient of each subgroup by the group that came before to be a simple group. So Z4 over Z2 is a simple group Z2. And if you like, you can dangle that quotient underneath the thing it corresponds to, just to help you remember. And you can do this in all three cases. So Z2 quotient by 0 is Z2, and Z20 quotient by Z4 is Z5. Okay, so we call this nested sequence of subgroups, a composition series. And we call the corresponding collection of quotients the composition factors. So this is our picture of a composition series for an abelian group. And our first goal is going to be to talk about something like a composition series for a persistence module. How will that go? Well, first, here's a Kroll-Schmidt decomposition of a persistence module. So this is a schematic picture. And of course, I'm cheating here by using a Kroll-Schmidt decomposition on the left to express the module in the first place. So the picture is a bit tautological. But if you don't use this, it's a bit hard to quickly specify what persistence module you're talking about in the first place. So we'll use the cheat. So on the left is a persistence module, which decomposes into 3 bars. And on the right is an explicit direct sum decomposition into those 3 bars. So there's Kroll-Schmidt. Any questions about that? Great. Now let's talk about Jordan-Holder. So as before, what we should look for is a nested sequence of submodules. So here's a nested sequence of submodules. And in the case of abelian groups, we asked the quotient of each submodule by the thing that came before to be a simple group. In our case, we'll ask that the quotient of each submodule by the thing that came before to be an interval module. So in this case, h1 modulo 0 is h1, which is an interval module. Similarly, h2 modulo h1 is another interval module. And as before, we can dangle this quotient underneath the corresponding numerator in the series, and we can do that for all the numerators, and we can get these things that we might call composition factors. Any questions about that? Let me make sure. Okay, I don't see any raised hands. Great. Anyone is welcome to unmute and shout out if they don't want to raise their hand. So we can't quite call these composition factors. They're not true composition factors, and I'll ask anyone to suggest a potential reason why. Of course, I've given it away on the slide. The reason is that in general, interval modules aren't simple. And if you'd like a briefly entertaining exercise, you can try to convince yourself that the only simple persistence modules, say in the category of abelian groups, are the persistence modules that are 0 everywhere except for exactly one point in time, at which point they become a simple group. So these things aren't composition factors. We don't have a composition series, and we should probably have a different word for it. So here's a different word. We'll call them secular composition factors. And similarly, you might want to call this thing a secular composition series. That would be pretty reasonable and systematic, but life isn't that kind. We'll call it something else. At least in the publication, and I'm not sure. In the slides at some point, we may change the name as well. But the thing to take away from this discussion is this clear correspondence between a composition series for abelian groups on the one hand, and something like a composition series for persistence modules on the other hand, where on one side we require factors to be simple groups, and on the other side we require interval modules. Okay, so we'll call this thing a subsecular series, and this comes from alternate terminology in the nomenclature of series decompositions of objects. And to review, a subsecular series is exactly what you see here. It's a sequence of submodules such that the quotient of each module by the module that came before is an interval module. I'll call this a subsecular diagram, which consists of the line of modules together with the quotients dangled off. And if you like, you can decorate this diagram further by drawing an interval next to each step in the sequence that says the start and the end point of the quotient module that you get. So A1, B1 are the start and end points of this interval. A2, B2 are the start and end points of this interval. And it can be helpful to have this written explicitly in a number of contexts. So this is just notation. Is all that okay? Great. So we say that these interval modules have support type AB if they start at A and they end at B. Okay, so here's a theorem. It goes like this. Take the collection of all intervals in your poset and arrange them into a sequence. Well, if your persistence module is valued in the category of finite dimensional vector spaces, then there's a nested sequence of submodules so that the quotient of each thing that came before is an interval module with the support type corresponding to that interval in the sequence. So that's a bit of text. Let me give an example. So I will pose a problem, and the problem consists of the following data. I specify one persistence module, and then I specify a sequence of intervals. And your job is to fill in all of these dotted boxes. In particular, we need to fill in S1 and S2 so that each quotient is an interval module, and it's an interval module for the interval specified in the diagram. Does that make sense? Great. Okay, so in this case, I claim that this is a solution to the problem posed by the picture on the right. So we start with S3, and we insert two submodules so that the quotient of each one by the one that came before has the right endpoints. Of course, this is a total cheat because I didn't tell you what the endpoints are. But if you imagine that I chose them correctly, then this works out perfect. So there's the theorem. I can specify any persistence module I'd like here and any sequence of intervals, and there will be a way to fill in these boxes. So we call this the subsecular series of the sequence of intervals that is specified here, the A1, B1 through AN, BN. We call this the corresponding set of subsecular factors, that is the factors of the sequence. And as you might hope, this set of factors is unique up to canonical isomorphism if your sequence of intervals satisfies a particular condition. So the condition is that your sequence has to be non-decreasing with respect to the partial order on intervals given by embedding of intervals into Z2. So what does that mean? Well, you can think of each one of these intervals as, instead of an interval, just being a point, A1, B1. And you can think about the sequence of intervals as being a map from the integers 1 through n into Z2. And you can request that map be non-decreasing with respect to the product order on Z2. Okay, there are many such maps in general. So there's no question that they exist. But if you select one of those many embeddings, then the corresponding subsecular series and the corresponding subsecular factors are unique up to canonical isomorphism. So that means just like a Jordan-Holder decomposition for abelian groups, the associated subsecular factors for this decomposition are unique up to isomorphism and permutation. How is that with everyone? Great. I love the audience feedback. Thank you, Radmila. Great, okay. So we're in good shape. And now that we know that we have a canonical way to associate a collection of interval modules with our module, we can define a secular barcode in the way that you might think is natural. A secular barcode is just a thing that takes an interval and it sends it to the secular factor corresponding to that interval. Okay, so there are several things to note and be clear about. This is not your ordinary barcode. So in particular, you're not sending intervals to numbers. You're not sending intervals to isomorphism classes of groups. You're sending intervals to other persistence modules. As you might hope, this does relate strongly to the generalized persistence diagram of a meet, which does send intervals to isomorphism classes of groups. So it's not wrong to make that association. As with the Jordan-Holder decomposition of abelian groups, this is fine-grained in the sense that we can break down things that can't be broken down by Kroll-Schmidt. In particular, there are plenty of persistence modules of abelian groups that you can't break down via Kroll-Schmidt into interval modules, but you can break them down this way, and it's lossy. We lose the isomorphism class of the module when we pass to these factors. Okay, great. So we've cleared the first technical hurdle and defined how these secular factors work, at least in somewhat familiar terms. Let me now present somewhat different terms, which are going to be less familiar, but super useful if you're interested in connecting with higher categorical structures. It'll be a bit of work. We're going to go through a theorem and a definition, but don't despair, we'll go through it step by step. And the key thing is that we're going to define a lattice homomorphism, and we're going to denote that lattice homomorphism by lambda. We'll construct it for any persistence module from a finite totally ordered set into an abelian category. And when I say lattice homomorphism, I'm referring to an order lattice, i.e. a poset with meets and joins, and will require that homomorphism to preserve the top and bottom elements. Here, m is equal to n plus 1, where n is the number of elements in our index category. And the domain lattice for our homomorphism is going to be the lattice of downclosed subsets of the Cartesian product. So here are two pictures of subsets of the grid. The one on the left is a downclosed region. The one on the right is not downclosed. So the family of downclosed subsets is closed under union and intersection. Those are the corresponding lattice operations for the domain lattice. And that's what it looks like. The codomain lattice is going to be the lattice of submodules of your persistence module ordered under inclusion. So it's a family of submodules, family of all submodules. The lattice homomorphism is uniquely determined by where it sends two families of downclosed subsets. So A cross M, this is a downclosed subset of M cross M. And it's going to go to a particular submodule, which can be defined by this formula, which is admittedly a bit opaque. But we can give some examples to make this a bit more digestible. So there's the theorem. We're going to construct this homomorphism. And now let me show you what this looks like in practice. Suppose you have the specific persistence module, which is indicated in this picture. So we'll imagine a linear persistence module that has 3 bars. The bar is shown here, and this is the corresponding persistence diagram. So the homomorphism that I've described, the so-called secular homomorphism, takes a downclosed subset of the plane, and it just looks at all the points in the persistence diagram that lie in that subset. And then it takes the sum of all those submodules of your persistence module. And by that, I mean the smallest submodule that contains each one of these smaller submodules. So this is a picture of what the homomorphism looks like, at least in one specific example. And you can write down a theorem that says this sort of representation works in general, at least if you're working with modules with field coefficients. So if you have a module with field coefficients, and you can break it down into a barcode decomposition, and you can look at its corresponding persistence diagram, this homomorphism does exactly what you see in the picture. It takes a shaded region, it takes all the bars corresponding to points in the shaded region, and it sums them together. How's that? Great. So we can't use this definition to define the secular homomorphism in general, because we're cheating by using bars to do it in the first place. But there is an important point to be made. This homomorphism is unique. It's uniquely defined. The decomposition of the module as a direct sum of bars is not. And one thing this theorem implies is that no matter what decomposition into bars you choose, this lattice homomorphism that you build out of it is the same. It's uniquely determined. So this is not at all obvious, or at least it wasn't obvious to me before I thought about things in this term, but it suggests something about underlying structure in these constructions and how these order theoretic constructions can pick up on something that that's perhaps a bit stronger than you would expect from the direct sum case. Okay. Let me just point out that you don't really even need to pass to subsecular series in order to get barcodes out of this homomorphism. So at least in the linear case, you can see that if you wanted to find out how many bars there are that run from 2 to 3, one perfectly reasonable thing that you can do is evaluate your lattice homomorphism on this light shaded downset, and then evaluate the homomorphism on the dark shaded downset that contains everything except the square that you're interested in, and take the quotient of one by the other. And we know by the structure theorem that I just said, that when you do this quotient, what you'll get is essentially all the bars that run from 2 to 3 quotienting out by everything else. So you can use this homomorphism to get bars in the linear barcode. The statement is that if you want bars in the secular barcode, you can do exactly the same thing. You don't need to go through subsecular series. You can just compute this one lattice homomorphism, and it will tell you everything. And in fact, there's a tremendous amount of data in this homomorphism. It extends, well, you can think of any lattice homomorphism as a functor between poset categories. And this particular functor extends to something called a p-exact functor from 2 p-exact categories, which are generalizations of abelian categories, which are non-additive. So these are places where you can do homological algebra because you have kernels and images, but you don't necessarily have additive structure. Okay. So one final point on structure, you can use this framework to run some famous results in the theory of persistence with non-field coefficients. So there's this result by Botten and Crawley-Burvey that says that if you take any totally ordered index category and you map it into a category of finite dimensional vector spaces, with whatever functor you like, you can break down the corresponding functor into intervals. And the corresponding statement is take any totally ordered set, map it into the category of finite abelian groups with your favorite functor, and that too can be decomposed into a composition series of interval modules. Okay, so there's definition 2, and it's a bit less familiar. People aren't necessarily as used to thinking about things in terms of order lattices, but it's very useful for making categorical connections. So I think I was told that I ought to wrap up right at the 40-minute mark, and I'll beg forgiveness for running a few minutes over to talk about applications, but we won't dwell on this too long.
That's perfectly fine. Take your time.
Okay, great. So let's talk a bit about applications. So we already talked a bit about interpretations of generalized persistence. So the idea of the generalized persistence module is already intriguing and interesting. It lets us turn this persistence module into a persistence diagram. And And again, points are labeled by objects in the category that you're mapping into. So if you have a persistence module of abelian groups, you get points labeled by abelian groups. And you might hope, well, let me skip over this. You might hope that if you have a persistence diagram of abelian groups, that might correspond to a secular decomposition, where sort of the objects in each interval module correspond to the objects in the persistence diagram. And this is almost true. You need to loosen things up a bit by saying, well, it's not necessarily going to be the case that you'll take the isomorphism class of the objects in this interval, and that'll correspond to this isomorphism class. But if you take the composition factors, the multiset of simple objects associated with this interval, then that multiset is indeed the decoration that you're going to put on each point. So the secular decomposition lets us interpret the generalized persistence diagram in a slightly new way. We actually can talk about a submodule that corresponds to a point. And by talking about things in those terms, we can map things back to data. And in addition, this fills in some gaps. So the secular framework can handle non-abelian groups, and it can handle vector spaces of infinite dimension. And the slogan to take away from this is that the generalized persistence diagram counts the composition factors in the secular barcode. So that's a slight oversimplification, because Amit's definition goes beyond just abelian categories, and when you do that, other interesting things happen. But if you take the simplest case of each construction, this is how they intersect. Okay. There are other scientific benefits to this way of looking at things. One issue that one commonly encounters in working with persistence in scientific data is the issue of reproducibility. So if you take a filtered space and you compute a barcode and you get a generator for it, what's to say that generator is unique? Usually nothing. And that can make it difficult to say, say you just run an experiment and you say, well, I found this really interesting cycle. This is where the interesting topology came from. How do you tell another person how to recover that cycle, short of just giving them your code and telling them to run it? There aren't so many ways. But the categorical structure that you find in homological persistence, and in particular the secular homomorphism, gives you a unique way to represent bars in terms of zigzags of submodules. So this is completely canonical, it's completely reproducible, and if you want to put in a scientific paper, this is what we computed and this is how we interpreted it. There's no ambiguity here. You don't need to say anything about your code or your algorithms. It's completely canonical. There are interesting connections with spectral sequences. In particular, the spectral sequence solves an extension problem posed by the secular persistence diagram. We can talk about this a bit more later if folks are interested. There are interesting connections with stability and multiple parameters. So this is not work that I have done personally, but it is work that people on this call have thought about. For example, there's recent work by Alex McCleary and Amit Patel on edit distance and persistence diagrams over lattices. This particular paper came out in 2020, and there's been a lot of interesting progress since then, so watch this space. And then, of course, as mentioned before, there's persistent homotopy. So any functor from a finite totally ordered set into group admits a secular decomposition. That means it admits a secular barcode and secular generators. We talked about this pair of filtered spaces earlier, and here are the corresponding barcodes for them. I guess we probably won't have time to dive too deeply into how these bars are calculated, but if folks are interested, I'm happy to stick around after or talk with you offline about how it's calculated. And again, this is interesting because this is a pair of filtered spaces that have isomorphic pointwise homotopy, isomorphic pointwise homology, and identical homological barcodes, but they have distinct homotopical barcodes. Okay, so there's a bit about applications. There's interpretation of generalized persistence, canonical feature representation for scientific reproducibility, extension theorems, edit distance, and homotopy. And in review, what did we talk about? We talked about a systematic way to decompose a persistence module into interval submodules. We didn't talk about how you can compute this decomposition by matrix factorization, but you can. You can use it to get generators. We didn't talk about algorithms that it suggests, but it does suggest a number of algorithms, in some cases, algorithms which are much faster for computing generalized persistence than what we had before. It solves extension problems and it presents new counting theorems. There are connections with various branches of category theory, quiver representations, etc. And the key ingredient, again, is this idea of exact non-additive categories. And it's worth taking a minute to reflect that Gabriel proved his first version of the decomposition theorem for linear coefficients back in 1972. And it took 50 years to get to the point of decomposing persistent non-abelian groups. And it's reasonable to ask why. Why did it take so long? I don't think it's not necessarily because people didn't care. I think people find ways of caring about these things. And I conjecture, you can't say why things didn't turn out a particular way, but I conjecture that part of the reason is that additivity breaks universal structure. And I won't say too much about that, but I'll give some hints. So when we construct our secular homomorphism, under the hood, our homomorphism really maps a semi-topology on the space of intervals in this poset into our target category. And it's an important structural fact. There's a so-called universal model, a universal category that factors through this map in a canonical way. And that universal model is really what we use to prove most of the structural results in secular persistence. And on the right is a quote by Marco Grandis, which concerns these universal models. And the key part of the quote is where he notes that if we let in additivity, then we destroy the distributivity of lattices of subobjects, the coherence of subquotients, and the possibility of any representations by lattices of sets. So essentially, when we let in additivity, we break the structure that we need to prove these theorems. And there's a tension between additive categories in the so-called projective mold and a different class of categories that fall into the so-called affine approach. The affine exact categories, I mean, both are highly developed, but the affine ones, including bar exact categories and proto-modular and a variety of others in that realm, they're heavily used in algebraic geometry and other branches. So it's very natural for the people who live in the world of algebraic topology, algebraic geometry, to work with those categories. But I think what we see from this example is that the projective world of non-additive categories has a lot to offer as well. So down the line, there's lots of work to do in this domain. There's lots of work with algorithms. There's lots to do with empirical studies. We don't really know what the statistics look like of secular invariance in data, in part because we don't have the algorithms, but these are being rapidly developed. There's a lot to ask about optimization and feature localization. So how do you work with generators once you have them? As well as what the algebra starts to look like when you start thinking about algebra with multiple parameters, as well as natural extensions, for example, to the case where you have an infinite index category. And I'll leave us with this again. I think there's a lot to be done with secular persistence, and there's a great deal to be done with this sort of family of tools in general. I'd be delighted to talk with anybody on this call about these things further. I think there's a lot of interesting work being done by this community, and I really look forward to seeing where it goes next. So I'll thank the organizers again for having me, and I'll be glad to talk about any questions folks might have.
Yeah, thank you very much for the great talk. Please unmute, everyone, please unmute yourself and let's clap together. Okay, great. So then let's take questions now. Who has questions? If you have questions, you can just unmute yourself and start speaking. Maybe I'll start with a question in the meantime. In the meantime, you can come up with questions yourself. Namely, I'm sorry if you already said it, but in the special case that your coefficients are set to, would secular persistence be exactly the same as persistence?
Excellent question. Yes. So it will give you essentially the same thing. So you'll get a breakdown into interval modules. And these interval modules, they don't have to be sort of one-dimensional. But for each interval, you'll get an interval module whose dimension is equal to the number of bars. So in all practical terms, yes, you recover the linear persistence diagram exactly. Good question.
Yeah. Thank you.
Oh.
Who wants to ask the next question? Okay, I'll go ahead and ask it another question because I have many. So you mentioned that secular persistence can deal with infinite dimensional vector spaces. Can you explain a bit more about what you mean there?
Sure. Let's see. One way to look at this. Come on. I accidentally left. Let me play again. I'll skip to the relevant part. Oh, I don't want that. Okay, so we talked about this so-called secular homomorphism. We talked about how if you have this homomorphism, you can compute whatever bars you'd like just by taking, essentially you can compute a submodule that contains Z and a submodule that contains everything except Z, and then you can take the quotient of one by the other.
Yeah.
The index category of this homomorphism, in this particular example, when you have a finite index set, well, this is a finite lattice. There's a finite lattice of downsets. And you really don't need anything about the lattice on the right to be finite at all in order to define this homomorphism. The homomorphism is just defined essentially in terms of a particular family of elements in this lattice, and you don't really need any structural properties at all about the thing on the right. So if your persistence module does have infinite dimensional vector spaces, it doesn't matter at all. And when you pass to an infinite dimensional index category, there are things that you need to be careful about. There are persistence modules out there, even linear persistence modules that you can't break down into a direct sum of interval modules. So you can find those pathological cases. But if you avoid some of those pathologies, for example, if your index category is totally ordered, then there's no obstacle whatsoever. You can have persistence modules of spaces that are as infinite dimensional as you like, and it won't make any difference.
Cool. So you can have infinitely many bars in the barcode with each bar can have infinite multiplicity and kind of still works out fine. It's pretty cool.
Yes, yeah.
So kind of it means that you don't need to work with, you don't have the restriction anymore that the function that you want to compute persistence of has to be tame, right?
Right. So as long as, if you have a well-ordered index category, then you can have whatever you'd like, and it will work out. And so I think one interesting direction to take this is to start thinking about, work that's being done in symplectic geometry recently, and some of these really nice results in Morse theory, where they actually have started correcting some famous papers by Morse and filling in holes by looking at the corresponding infinite dimensional persistence modules.
Oh, cool. We have a new question that just came in from Zvi Rosen, namely, where is the name Saecular from?
Right, another good question. So traditionally, secular means not religious, right? Wrong. Secular is I'll tell you the fun story. In ancient Rome, there was something called the Secular Games. And it came from this interesting myth about an old man who lost his son, and he made a deal with the gods to bring back the son on condition that the man would throw these sort of fabulous games, sort of like the Olympics. And the deal was you have to throw these games once every 110 years. 110 years is a seculum. And the idea was that that's a long enough period of time that no human would see two of them. And the word secular is tied to the notion of birth and death and only ever seeing one of these things. And in practice, the way this turned out in the empire is that every emperor wanted the prestige of throwing a secular game. So they would strategically choose different calendars each time they got a new emperor. And in practice, you'd get a secular game every 5 to 15 years. But that's where this came from. The notion of a seculum is tied to birth, death, and intervals.
Thank you very much.
Oh.
Okay, who wants to ask the next question? I can ask yet another one. I want to give other people also a chance. You described this finding generators using this zigzag. Can you maybe explain a bit more about that?
Sure. Let's see. I'll try not to leave the slide this time. So the nice thing about this framework is that, let me see, am I actually going in the right direction, or do I need to go the other way? As I said, when you drop additivity, which incidentally means you have to leave the world of abelian categories. Somehow abelian categories have too much structure. And one of the ways that this shows up, an easy way to think about it is if you look at the family of subspaces of a vector space, and you look at canonical isomorphisms between spaces. So suppose you have two planes that are slightly off kilter. But there are ways that you can construct isomorphisms between them just by quotienting out another subspace, and this will canonically identify them together. You can get lots of homomorphisms between subspaces in this way. And the problem is that if you do this, the family of homomorphisms that you can get to connect to subspaces is really complex and really large. And this makes it hard to get a grip on things. But if you drop some of the structure, it turns out that you dramatically reduce the space of possible homomorphisms. And you start to get things that are canonical. So in the secular framework, again, this is the secular homomorphism. And each time you evaluate it on a downclosed set, you get a submodule. And essentially, by restricting to this, this smaller category, you drop the space of possible maps between things. And you drop it so much that there starts to be only sort of a unique way to connect two things by a zigzag of maps. And that zigzag can sometimes correspond to a subquotient of your module. So for example, when you play this game of quotienting one thing by another thing to get an interval module. So this is how that canonical representation shows up. You get these sort of unique zigzags. And so it's not necessarily that you get a unique generator, it's that you get a unique series of maps, which is very true to the spirit of algebraic topology generally.
Yeah. Thank you. Okay, then if there are no last questions anymore, I will stop the recording and then you can still ask questions in private. Okay, and stop the recording here. Thank you again.
Great, thanks so much for having me.